Yeah. So before we continue, I want to quickly recap what we went over previous class. I don't know how many of you had a chance to read that, but in previous class, we talked about reinforcement learning, and we basically, a bit distracted. We started basically with definition, and we said that, well, the idea in reinforcement learning is that we want to we have some downstream goal, which is maximizing some reward, and we want to basically be able to estimate that what's the best policy, what's the best set of action we should take in order to reach there. And the first thing we defined was like the definition of value function. Value function basically tells you that the state, the position that you are in at that moment, how much it is worth. Right? That's a value function. It basically gives you a sense of estimating how good is an estate. If I take an action and I go there, how good is that place, for example? And the first way of this basically defining value function was Bell's band equation, which technically has, here you see two ways we are basically showing it. One is that there's an expectation over the policy. You have a reward, immediate reward. You have a discounted future, like a values. And then also we can basically represent it in this form. And here, the way that in the second scenario, basically we are saying that, well, there are all sorts of action I could take at this position. So it's going to be like a summary or a summation over all possible actions that I can take. And from that action, there are all after taking that action, there are all possible states that I could enter, and every state basically gives me some value. So here this is going to be the second thing for the all possible states that you go to. Each state has a probability of you could go to. So that's kind of like a weighted average, basically. And then we say that we also have this Bell band optimality equation, which is what's the what's the maximum reward, best scenario this state could give me, best value this state could give me. And that basically is that, well, when I'm here, I could take all possible actions. And based on that, I could get different rewards or different basically total accumulated reward. The best one is basically is given an action that gives you the maximum, basically. You know, instead of looping across all possible actions and doing average, you basically say that the action that gave me the total maximum value, that's basically is going to be my output. So then we talk about something that when we go to this reinforcement learnings, one way of looking at the reinforcement learning is that model-based and versus model-free types of model. So model-based algorithms is the scenarios that when you have a definition of the model of the environment, dynamic programming, for example, right? In model-free is the scenarios like when I don't know about the environment and I want to interact with the environment and learn from it. Two of those basically are MC, Monte Carlos, and TD learning, basically, which we talked about. Now, in general, anytime that you have this value here, this transition probability, the chance of going to next state, that requires having a knowledge about the state or environment. But most of the time, we don't have that knowledge. We don't know what's the chance of if I do this, I will end up in the next place. Okay, so basically, in order to get rid of this scenario, because there's a probability. Having this probability means that you actually know the distribution of all possible probabilities. And we said that one way in order to get rid of this dependency is using Monte Carlo, which basically anytime there's a distribution, instead of actually dealing with the distribution, you sample from it. Now you have the data. Now every data point in that sample has the same probability of occurring. So that's why when you go to Monte Carlo, the value function has these terms behind it, because technically, if you have 10 possible states, that means 1/10 multiplied by anything, because every state has 10% chance of basically transiting to. So that becomes the Monte Carlo for value function. What you see here, this first summation is across the samples that you take. If you take 10 samples, the inner part is within one sample. If I take one sample, Monte Carlo requires a full trajectory. That means when you take one sample, you start and you need to repeat the experiment until you reach to the end goal. So this is what it means. to loop across all possible outcomes until you reach to the end goal. In one scenario, you might solve it in 2 steps. In one scenario, you might solve it in 1,000 steps. It's kind of like until you reach to the end of the trajectory. So it basically, you do some weighted sum over this, like a discounted sum over this rewards across this trajectory, and you repeat it for 10 times, for example, and you average those together. That becomes the value of one state. And you basically learn it by just doing sampling. So that way you don't have that probability, transition probability. You don't need that anymore. Now, so this basically also the same thing. So you can update the previous estimate that you have if you want to do. So in this example, in Monte Carlo, you repeat all 10 experiments through the end and you average it. In this example, incremental update, I don't need to do all 10. I do one at a time. Every time I have a belief, I update it and I start a new next example. I go to the end, I get some values, I update it, and so on. So instead of waiting for all samples to finish, you do 1 sample at a time, 2 samples at a time, basically, and you update. And this update basically says that whatever was your previous belief, which normally you can start by 0, for example. My previous state value was 0, plus some step size, and this alpha was similar to learning rate. Here, a step size is more like how often I have landed here, just 1 over that, basically. How often you visit a state. And this GT is this term. This is called GT, which is the total reward from the moment you start to the end. So that's GT, basically. That's like a full reward for the full episode. And then minus your previous belief. So that basically, that becomes an incremental update. Is that clear so far? So then we say that, well, in Monte Carlo, it's also kind of like you always need to go through the end of the episode. You need to do a full trajectory. And that's not also itself optimal. Could we do something about it? Could we not go through the end? Then that's where it becomes TD learning. So TD learning says that instead of going through the full episode, you basically do 1 step at a time and you just bootstrapping. And you do update and you go to the next episode and so on. So TD learning for the same value function, basically the equation changes that your previous belief plus that step side learning rate. And you have this term, which is called TD target. Okay. And TD target basically is that from the state when you took an action, the immediate reward plus discounted value of the next state that you are going to. Okay, so that's the TD target. That TD target tells you that I'm right now here, I took an action, I got this much immediate reward, and the state that I'm landed, it's worth it, for example, 10 points. I sum that as an immediate reward plus discount factor gamma times that the next state's value. That becomes my TD target. All right. TD target minus your previous belief about the state that you were in. Okay. Now, what does that tell you? At every step, you incrementally bootstrapping, you're just taking 1 step and updating your previous belief. When I'm here, I believe that this state is worth 10 points. Then I'm like, okay, I believe this is 10 points. I take 1 step, I get 2 rewards, and the next state that I am in it is like 14 points. So previously I was believing if I'm here, I have 10 value. I took 1 step, I got 2 rewards, then the next state that I'm in is worth 12. So now you basically do 2 plus gamma times 12, okay? Gamma, let's say, is, I don't know, it's like a 0.9, for example, times 12 plus 2. That value becomes your, so you were believing that the state that you're in is only worth 10. But now you saw that if I'm in this state, I actually could acquire more than that. So that TD target is the next target basically you could achieve. So what you do target minus your previous belief, and that becomes TD error. How much you were wrong technically? I was believing this state is worth 10, now it's worth 11. So I was wrong by 1 point. So you bring that 1 point times the step size plus the 10, that becomes your new belief for the current state that you are in. So instead of going through the full trajectory in order to update that, we You do one step at a time, bootstrapping, update. Now you're in the next state. Next state also similar. You have a belief, you take one step. So instead of, again, doing everything through the end, you just repeat one step at a time, and you repeat this multiple times, multiple samples, similar to Monte Carlos, basically. It's not just one example. So you do, let's say you do 100 samples. Every sample, let's say it has 20 steps, mini steps, basically. So instead of going through 20 and update, you do 20 incremental updates, and then you basically continue the sampling. Okay? So that's the TD learning. Then we also talked about Q function, which is value function by default only tells you that what's the value of a state that I'm in. Q function tells you that how good is this state if you take this action, basically, in this state. It's like you basically have the state and action together. Okay, so that becomes Q. So, how good is this action if I take it in this state? And then that's also, this is the same things using the TD learning function, whatever previous belief you had, TD target and TD error. Okay, and you also could show the Q function in this form, becomes an expectation over all possible rewards, because again, rewards could be, they are not always deterministic. It could be a stochastic reward. So become expectation over reward plus discounted feature values. You could also show the Q function this way. You know, there's different ways that you can show it. Expectation over discounted rewards, and you repeat that across all the trajectories, basically. And you still here, you go through the end and come back. Okay. So there are different ways that you can present those. Now, okay, any question before we continue? All right, so now let's again go over the value functions, state value. So for Bellman optimality, there's a scenario. Basically, we define this maximum. Look at the state values, like the maximum over this value given the best action, basically. So the maximum over action. So that means you want to take an action that gives you this maximum, gives this value as the maximum for you. Now here, this part, you have a summation over R. That's for the scenarios where the reward is stochastic. That means I could get $5, I could get $10 if I do this. So you do an average reward, basically. There's a scenario when the reward is deterministic, then you don't have this part, you just directly have the reward. That means if I'm here and I take this action, I always get this value reward. It's going to be fixed. So this term, you know, if you think about any basic expected value, it becomes like when you say expected value over the reward, you technically have summation of reward times probability of that reward. So if it's deterministic, you don't have this. You just have a reward. So that's why this multiplication disappeared. We only have a reward, and we put the reward here, basically. So it becomes a summation over all possible states. Every state, there is a chance that you go to that state. There is a reward, deterministic reward, plus there's a discounted value. So if it's stochastic, if it's deterministic. And same thing goes for the Q function. Basically, you could have, for action value, basically, you could have a stochastic scenario, or you could have deterministic scenario. And both of them, as you see, the only difference here becomes Q over there was V, and here this becomes Q star over there was V star, right? So most of the ones. The goal here is that you just understand if it's deterministic or stochastic reward. You have one summation extra in one, the other one you don't have that. And if you want to find optimal value, so for value function or state value, you basically becomes the maximum of action value. So here is that if you find optimal of that, the action that gives you that maximum value becomes the state value. And then optimal policy becomes an argmax. Becomes policy is the action that you need to take in order to reach to the maximum. So you do argmax, so you get the action back, basically. That becomes the policy in order to get the maximum reward or maximum value. So now to just summarize the Monte Carlo, you always basically start something like that. So you do a policy execution. So you have a random policy. You do a policy execution. What does that mean? That means I randomly pick some actions. You know, the sample from my policy. I pick some actions, and I execute the policy. That means I will take the actions and I will write down the outcomes. I took this action. I landed this state. I received this reward, and so on. You basically create a trajectory. Then, and that becomes this. The second part. Then you calculate the returns, and again, return becomes, remember for Monte Carlo, you need to go full trajectory, and that's the full trajectory. Immediate reward plus discounted for the next and every basically a step or along the way, the basically reward for that state becomes less important because the discount factors become basically larger. So here basically what we have. For given a state, so T here is a given state. What does that mean? That means if I'm here and I take a full trajectory, that's the value for this function. Now, if I go here and I take a full trajectory, that's the value for this function. So every basically a state or basically every location that I get one reward function. So then when you have that GT or the full basically return, you go and update your Q. What was your previous value, which again, as first you initial all of those to be 0. What was your previous belief plus you got some reward, you do some update, you add some basically learning rate to it, and you update it. And now when you have that, you basically go update your policy. So whatever action you took that gives you the maximum Q, you pick that action for the next timestamp or next episode, basically. So that way this is the optimal policy. The best policy, not optimal. We haven't defined it. So that's MC. Now the next thing comes. It's going to be Q learning. So Q learning is a TD control algorithm. It's going to be model free and it's going to be off policy. So model free means that we don't have the information about the model. We don't have information about the environment, so we just interact with and basically get the results. Off policy means that, so we will see also this one. So we have off policy, we have on policy. On policy means that you always take action based on what's the policy. That's basically on policy. Look, you have a fixed policy and you take action based on that. Off policy, that means that you take an action not with respect to your policy. It could be based on what gives me the maximum reward. What action gives me the maximum reward? I will take that. In on policy, you always ask your policy, what should be the next action? Okay, so just kind of like the way that you take the action is going to be different. Now, so in Q learning, in the general form of Q learning, we have this table called Q table, which basically you define for all possible states and actions. You have these Q values. And then you choose an action, you perform an action, you measure the reward, you update the Q table, and you repeat this process over and over again until you get to the point that the table doesn't change anymore. Now, so this is going to be the equation and the example for it. So if you're looking at what we have here for the Q function and what we have there for the basic Q learning, the only difference that you will see is this maximum term. There's a maximum after the gamma before the Q. And that's come back about the off policy. In on policy, you pick the Q is generated based on the action that you took from the policy. In off policy, basically what we are saying here is that I took a step and I went to a next state. I received an immediate reward for that action that I took. Then I go to the next state. Here, this value says, what does it say? It says the Q function or Q function or Q like a state action function for the next state and given an action in the next state, basically. So if you think about it, what it says is that I'm here, I took an action, I'm here, I took this much reward. Then basically the discounted value for the next state comes about if I'm in the next state and I took a certain action in that next state. Because that Q over next state is itself has an action. In here, when we have a maximum before it, we say that we always assume if I go to the next state, in the next state, I always pick the best action that gives me the maximum. It's a maximum or an action. Instead of going to the next state and take an action based on whatever is your policy, when you go to the next state, you only take an action based on which action gives you the total maximum return. So that becomes off policy. Because again, on policy, you take the action with respect to policy. Off policy, you are kind of like, no, when I want to take an action, I only pick the thing that gives me the maximum reward. I don't care if the policy says something else, basically. If the policy says go right, but based on my understanding, going left gives me the total maximum reward, I go left. You see, that becomes the off policy versus on policy here. Yes.
So in this, let me just take the right and left example. We choose to go left because the next step after going left would give us the maximum value.
No, I'm talking about, so this is the next state. So let's say I'm here and I go to the next state. In the next state, so that Q value tells me that if I'm in the next state, Q, so what you see here is Q S prime A prime, right? What is the value of Q, basic Q value? If you're in the state S prime and you take a certain action, okay? But the certain action, it's not an action that you know, right? Here in this scenario, it could be some action. Okay. In this form, we basically say that instead of saying certain action, I only take the best action in the next state. So you always act optimal with respect to which action gives you the best reward or total basically return in the given state.
Sure if I follow.
Okay, so if you are in this state, okay, ST, and you have this value Q, ST, and AT. You took an action, correct? So given the action, you are going to here. ST plus 1. Okay. So if I tell you what's the Q value for this state, and you're like you're basically using a TD learning, and you try to update that, you are saying that I previously believed this state has a Q value of 2. Okay. So my new Q value is 2 plus some learning rate times some learning rate times, when I went from here to here, let's say I received reward of 1. So it becomes 1 plus, I leave this part empty, minus the 2 itself. Okay. So now this part, in the general form, what we basically say is that when you go to this state that you have, by default, this state also has ST plus 1 is, but you don't have one action. If you think about for this state, you have a table. Basically, you have this Q ST plus 1, and these are all possible actions that you can take. Correct? So depending on which action you take, you have a value. Correct? So here, when in the general form, when we say Q ST plus 1 and AT plus 1, that AT plus 1, the action, is not that you pick it, it's come from the policy. That means when I'm here, the policy that I have, policy is stochastic, it could tell me pick action A2. Okay. Correct? So whatever is the value that you see here, it comes here. In the Q learning, instead of listening to the policy that tells you which action to go, I do argmax among this,
Okay.
and I pick which action gives me the maximum value, and I only pick that.
Understood.
So instead of listening to the policy, you just pick the maximum, the one that gives you the maximum value. So, yes.
But logically, this makes more sense than listening to policy, right? So why do we pick this? Why do we not pick this our policy?
Well, you can always also diverge, like if you do something like that for a local divergence, and you can easily go sidetrack, right? So, all right. So, yes.
Sorry, this is a little bit back into the course, but
Yeah.
this is mind-boggling a little bit for me. But when we say QST-AT, if we take action AT, we are not anymore in a state ST.
What's the value? Like basically, what's the return that we have if I am in a state and I take an action, certain action?
And I'm not in that state anymore.
But you still being here and taking an action, right? Based on where you at. If I'm here, I can go left and right. If I go to next state, maybe I cannot go left and right. So it's really important with respect to where you are at. When you take an action, so if let's say you are at home and you have two options. You either go to a school or you sleep, right?
Mhm.
So you have two options, and those are the actions. When you go to a school, you don't have those two actions. You have different actions.
Yes.
So the reward the cue that you receive for when you are at home and you take an action to sleep
Yes.
is only based on the states that you are in, not the next state. If I decide to sleep, what happens? That means right now I will get 2 points because of sleeping, and I lose 8 points because I missed the class. Next state value.
Mm.
So it should be always with respect to where you at, what action you take, not where you're going to go, and because you don't know where you land if you take an action. That's kind of like a stochastic. In the scenarios which is deterministic, you're like, if I go left, I go left. Yes, but in the scenarios that you don't know the environment, you try to go left and wind blows you, and then you go some other direction.
But the way you frame it, it's like it's independent of the action.
No, it's not independent. So
Because you just said, if you are in the state, and I got confused in the state and actions. Okay, never mind.
no, so okay, if you are here and you're like, I want to see what's the value of this state. Okay, you can directly calculate using V. Okay, which the difference is that V is just directly looks at what's the value of the state. Correct?
It's a number.
Yeah.
Scale.
Another way looking at it is that, well, in order for me to tell you how good is this state, maybe I should see what are the possible actions I can take at this state. Okay, so you have, let's say, all these possible actions that you can take. Right? So when action comes into play, you need to also take action into account. So you use Q, right? Basically, Q tells you that what's the total reward, what's the value you have for this state if you took these actions. So you calculate it for all of this, and that's why when we say the value, the optimal value for a state is maximum across all possible this. Across all of this, you pick the one that gives you the maximum value, and that's how you say how good is that state, because you know in that state there is an action that gives you the maximum value. Right? So that becomes the optimal value for that state. Does that answer?
It's better, yeah.
Okay.
Gonna stay home
All right.
Now I'm confused.
Okay. So maybe you two need to, like an LLM, to start talking to each other.
So I'm looking at the equations from Bellman's and the Q, which is dependent upon state and action.
Mhm.
So Bellman's is the average over all the actions we can take in a particular state. I'm getting that
Bellman-
correct.
Okay, you're talking about this one.
Yes, Bellman's equations,
Okay.
yeah, the value function. At a particular state is the expectation. Basically, it's an average over all the states that I can go to if I take a particular action, right?
Yeah. That's Bellman value.
That's Bellman value. So the QS of A.
So first, Bellman value is an average.
Yes.
Bellman optimal is not an average.
Yeah, it's not an average.
Right?
Yes.
So here what we talked about, Bellman optimal, which is not an average over Qs, is the Q that gives you the action that gives you the maximum Q, right? So that becomes the maximum value. We are not talking about the Bellman, we're talking about optimal,
Oh yeah.
right? So there's a difference.
Yeah.
Optimal versus average,
Average.
basically, expected values.
Yeah. I'm back to that.
All right. So now, here the next thing here is when we do with Q, there are two things also we're going to talk about is exploration and exploitation. But first, if you want to update the Q, so you initialize the Q values as we just talked about randomly, you set all of them to 0. You define some convergence condition or basically number of iterations that you want to loop, take an action from a certain state, basically watch how much reward you receive, what's the next state that you go to, you update like using a TD because it's like a bootstrapping one step at a time, and you basically move to the next state and you repeat. And you just let this loop basically run, and that Q tables that you have basically at certain time, hopefully you get to convergence. Normally for a smaller types of model, not for larger environment. Now, the challenge that you will end up have is deciding between exploration and exploitation. So exploration, let's start with the other one. So exploitation basically is this, when you want to take an action, if you always look at which one gives me the maximum value, that means every episode, if you come back to the same state, you're always going to take the same action. Because you always like, this action gives me the maximum value, and I already know they're acting greedy with respect to that. The problem with models like that is you never see the possibilities of other actions. Maybe this is right now gives you the best action, but if you explore, maybe you're going to get a better result. So that's the concept between exploitation versus exploration. Exploration, you allow the model once in a while, take a random actions, repeat it through the end, for example, see what's going to happen. Exploitation, you always basically act greedy and always take the same action over and over again. Okay, so now that comes to the next basically model. It's called SARSA, and a state action reward a state action. That's what's the name comes from. Okay, so this one is an model-free and on-policy temporal. On-policy means that you don't pick this based on the one that was argmax. You take the action based on whatever the policy tells you basically to take. Okay, so basically same concept, same equation. The only difference here is that, you know, the steps are a state, that you are in a given state, you take an action, you see a reward, you go to the next state, you take an action. So that's 5 basically steps that you see in the name, SARSA. Now, in SARSA, we introduced the concept of epsilon greedy, and that helps you with the concept like exploration versus exploitation. So you have this epsilon value that's kind of like this is like a chance probability. With the probability of, I don't know, 20%, you explore when you are trying to pick an action. It's like you take a sample, like a random generation. If it's 20%, I take a random action. If it's 1 minus epsilon, I do exploitation. That means I always take the same action that I knew and I know it gives me the maximum reward. So that's basically how you help with exploration with exploitation. So it's SARSA. Again, we start with the table, take an action, observe a reward, go to the next state. When you are in the next state, in order to take the next action, you're basically using epsilon greedy policy. That means there's a certain chance, high chance that you still pick the maximum, the action that gives you the best reward, but there's also a chance that you explore. So then you update your Q value again, you go to the, change the S to, and S prime to the new ones. Basically, that means you went to the next state and you repeat basically. So that becomes SAR. So you just do some epsilon greedies. Yes.
My answer might be wrong, but like I think last class we said that to set a policy, we do a lot of exploration first, and then based on that, we set a policy. So once if a policy has already been set, that means exploration is already done. Then what other exploration will be done?
No. So I don't think we said that we will set policy. Lots of time is that you, like, if you think about the whole idea of learning here is that to find the policy. If we know the policy, then we don't need to do reinforcement learning. Because if I know every time what action should I take, then you have the solution, right? The idea was that you set the policies, maybe, I don't know, just random at first. And then you repeat through the experiments, you take an action, you monitor, you update your values, and based on those values that you have, you incrementally update your policy toward a better and better policy. When you incrementally update your policy, what happens? Your policy goes toward taking an action that gives you the best reward. Right? So that means next time when you go back to this state and you want to take an action, you look at the policy says you go right. But what we say here is that with a certain probability, if the policy tells you go right, go left. To do some exploration, to see, just try to see what's going to happen. So you do some of those explorations, and sometimes you actually end up being a bit much. Even if you think about concept of a gradient descent, you can easily go to a local minima and get stuck there because you always you went a certain path line. And what would you do? I redo the process. I basically started maybe from different starting initial. Or maybe if I feel like I'm stuck, I take a random jump to get out of that local, towards certain basically degree, increase my gradient value, right? This could be something similar to that, not necessarily the same, but just says that if you always take the same actions, then you basically end up with the same results.
So in this equation, should we incorporate the probability to distribution of the action?
It's not written, but this is basically what it means here. That means there is a distribution, there's a chance that
Action will be coming from that.
Yeah, it's not distribution, it's technically two values, an epsilon, 1 minus epsilon, it's a probability. It's like if you get like a binomial, all right? So you have, you can write that distribution. You have a binomial, you have a theta, 80%, you always take the same action, 20% you take a new action. So
What if, let's say in a particular state, there are a lot of actions that I can take in a particular state, then there needs to be a distribution that covers that actions, right?
Yeah, so think about this. So if I have hundreds of actions. If I'm in this state, one out of those 100 gives me the best.
Yes.
So if I always do exploitation, I always take that, irrespective of the 99 other that we have. What epsilon gradient tells you that is not about how many others you have. It's like a binary. You either do exploitation or you do exploration.
Yes.
So when you went to exploration, you just randomly select.
Okay, so I'll pick randomly one of the 99 ones.
Yeah, pick randomly. You want to explore. You don't want to be greedy about selecting. You just want to let the model to try out. Okay. Because otherwise, then you end up with another basically greedy steps over those 99. Okay, so this becomes SARSA versus Q learning. In SARSA, policies is on policy. Q learning was off policy. That means again, you update from hypothetical optimal actions, right? Because it's also important to remember when we say hypothetical, but we don't know actually if we have the best action in the next state. You assume that whatever I do, next state, I will take the best action. It's kind of like in some hypothetical basically assumption. And for update rule, basically you use this one. The only difference here, there was a maximum here. And this basically in SARSA exploration, it comes from some epsilon greedy. In Q learning, there's no exploration basically, because we always assume the optimal decision. So always I know I'm going to take the best actions. So Risk behavior SAR, so it's more conservative. It's because also it does some exploration. Q-learning is more aggressive because it's always like taking optimal actions. Now, it's just an example. I think you have it in your PDF, but also try to solve it. So see if you, based on whatever you have over there, if you take action, will you catch the big piece of cheese or will you take the poison, basically? Yes.
In SARSA, let's say it goes exploring, it finds a better way, it updates everything, and updates the policy. And right now that policy remains the same. While exploring, isn't it like not efficient if you just give a random probability and it explores the same path that it has already taken and the policy was updated?
But it's not already the same. Remember, as we sequentially going, you update the values of each state.
Yeah.
So previously, maybe you took this action at this state and your estimate was 20. But after a couple of episodes and iteration, other states along the trajectory, the value also has changed. So a discounted return is not going to be the same in compared to last time that you were here. Because at every time, if you think about it, you start first randomly give value to every state. So whatever, if I'm standing here, whatever estimate I have at time t equal 5, versus when I come back here at time t equal 500, they should be different. Because it's the basically expected total reward at this time versus some time stamp later, it should be different because those states along the way have been updated also. You know what I'm trying to say? So at first, every state, let's say, has a value of 0. So expected total reward, it just comes from the immediate reward that I received plus zeros. Now, let's say after lots of iteration, now every step along the way has some value. So if I'm back here, I take the same action, the immediate reward is 2, but now plus the discounted reward, those are not 0.
Okay.
So your value is going to be much larger than previous time.
Yeah, but at the same time, when that probability hits and you go exploring, is there any chance that it might take the same, like a previous explored value is what I was asking?
I mean, it's possible. It's a random selection, right? But so you need to also keep this in mind. You don't do this just one time. It's actually when you do exploitation, it doesn't mean that you just explore once. You actually have a certain degree that you will explore. Okay. It's not just one time because one time won't be enough. Right, so basically you let the model, maybe 20% of the time the model explores. And if your model runs for, 10,000 epoch, you basically have like about 200 times that you can do exploration. And hopefully among those 200 times, you gain something insightful that next time one of those is actually part of your optimal action. Right, it's like that's the idea. Maybe not also, it's not like it always will lead to optimality, but it's just you want to be sure that you don't just do the same thing over and over.
Is there a best of both worlds scenario, like SARSA and Q-learning?
We'll get there. We'll get there. All right. So now, challenges in Q-learning. Well, the first thing is that table-based representation. You always need to have these Q tables, and that it's going to get out of control, especially when you have the large dynamic, basically. Then also it's for the generalization, if the agent goes to a place, and because you always do based on this table, if there is an action all of a sudden, because there's an environment, there's something happens that you haven't seen before, the model doesn't know what to do, basically. There's like you go to an state and you're like, based on the environment, there's certain action you need to take, but you haven't seen that before, you don't have any update over there. So that also could be another problem. Now, the solution to this Q-learning was, well, let's start using neural networks. And that's probably, if you have heard deep Q networks, that's like the types of basically model that you basically do Q-learning, but you use neural networks, in order to determine the policy, in order to determine the action that you want to take. And this has been used a lot in gaming, basically. You basically try to teach computers to, or basically an agent to play games, Atari games and stuff like that. It was really popular at first for those. And basically the idea behind it is that, well, you are in a certain state and your state has certain representation. So you represent the state with a vector. And that vector has series of information about that state, okay? Then you, instead of using Q function, Q, you use G. G is approximation of Q. G is a function, is a neural network that approximates Q. Okay, that's basically what it means. So G is a neural network that has a parameter W, and S, which is the state as an input it will receive, and will predict the Q value for you. So instead of having the Qs, you are using a neural network and says that I'm in this state, what's the Q value? And the model based on the state, it will give you an answer basically. So that's one example of the Q learning or deep Q learning basically. So you want to teach a model to do Atari games. So you have this screen, like the game screen. You do a series of convolution, and in order to understand, to learn basically the image, the videos basically that you have. And you bring here, you have this fully connected. On the last layer, basically you have the actions. Okay, left, right, this, press this button and do this or so on. And you pick one of these at the end. Basically, it's like there's a probability, like a softmax, right? And basically you take the action produce a reward, or basically you either lose the game or you basically the game is good, and you take that as a feedback and you do back propagation on the network. So the only, instead of you keep tracking of all those Q values, you just have a neural network that you do back propagation through and update the parameters of this neural network in order to help you with making the best decision. So you basically get rid of that policy, manual policy definition. Is that clear? This part, everyone's like, yeah. All right. So now, in order to define this deep Q, instead of having one neural network, there are actually two neural networks in it. Okay. So, and that comes back. So, if you're looking at this Q function, okay, so we have, there are technically two values here. One is the Q, okay, which we want to estimate it. How good is basically this state and this action? And basically this Q value, we have a neural network for it, parameters with W. The second one is this target, the Q of the next state, technically, you know, or that target value. So we also do that with another neural network. So you have two neural networks. One of them is going to predict this one and this one, they're the same. One of them is going to predict this one. Okay, instead of having, and technically in the first version, they didn't have two, there was only one. In the second, iteration, we introduced basically like two network, you know, it just helps with the convergence. So, and then you have this loss function, and the loss function is technically this, TD error. So the error between your Q plus that TD target, and you do a square error, you put 1/2 behind it to just cancel out. So that becomes your error function. And you want to update W, you basically do a gradient descent with respect to W. It's important to remember, so this one, I think I'm missing something. So this is supposed to be also W prime. This is not the same W. So that's why when you take a gradient with respect to W, this term doesn't have a gradient. Only this one has. So this should be W, I think the prime, it wasn't supposed to be on Q, it was supposed to be on W, okay? So, and then you update your W using gradient descent. You go to the next state and repeat this for some iteration. And now the question here is that, well, what about the second neural network? Okay, So the way that we use for Q is that at first, this one is equal to that one, same weights. Then you repeat. So you technically repeat the iteration for a certain number of times, and then we update the parameters of the target network by setting them equal to the parameters of the other model. So the models are the same shape. One of them, we iterate over only on that one, we update it. The second one, we don't update it directly, but every maybe 10 epochs, every 20 epochs, we set the parameters of the second one equal to the parameters of the first. That's equivalent of an update, basically. Okay, because the first one technically has learned what's the optimal policy. Second one is also technically does the same thing, but just for the next state. So we can do a transfer learning of that knowledge from the first one to the second one. So that's the idea here. Now, there are a couple of challenges that in the first paper that we had, and was the instability in the gradients. There was lots of divergence, obviously unexpected behavior. So the solution was two things. First one was the dual network approach, which we just saw. Instead of one network, they introduced two networks. The second one is something called experience replay. So the idea in experience replay is that every time you do something, you keep track, you basically create this history of things that I have done. Now, if you're looking at this chart here, this is the Q value, and here basically we have the states. So the blue line that you see, basically you're in a certain state, you take an action, the Q value goes up. Now the next action, basically what happens, as you see this line is basically goes down, what happens here is that the actions are kind of correlated. Basically, it's kind of basically because the states impact each other, right? So you might end up basically going on a really smooth path going down. So in experience replay basically says that you have some idea of past, okay? Once in a while, instead of listening to the model, you randomly pick something from past and say that, well, I want to do that action. So if you are going down, instead of going here for this action, you randomly pick this action. You look at the previous history and says that, well, I want to do from experience, I want to take some action like that, basically. I'm going to go there. And then you repeat. The goal here is that to break the correlation between steps, basically. Because otherwise the steps are that sequential happen after each other, the states impact each other. There will be some correlation in the values. So in order to break it, you have this history and randomly select from that. So this becomes the overall basically steps in deep Q network. So you initialize this buffer zone that is empty at first. You have the Q network with parameter W. You have a target network which gets the parameters of the same one. You basically do some for every, so you do some initialization. I'm starting at this state. That becomes the initial state. You take an action using epsilon greedy, pass that to this network. Then based on the action, you get a reward. You go to the next state. You do save this transition. A state, basically action, state, reward into that buffer zone that you have for later. You do sample, so once in a while, basically you sample, this part's supposed to be once in a while. You sample randomly from this for the next state that I want to go. You compute this TD, and then you calculate the loss, update the gradient, and repeat. And once in a while, you update the parameters of this third model, basically the second model, to be equal to the parameters of the first model. You basically just kind of like a neural network of loop, basically just you let it happen, right? So this types of model tends to play really good in like games, but also in AlexNet, one of the top CNN basically models, image classification models, basically is AlexNet, or you can use it for transfer learning and stuff like that. And last part of this model is a deep Q network, basically. So up to this point, it's just the CNNs, and they basically add some deep Q networks to it. So basically, model basically learns to take certain actions or certain decisions based on some learning. It's more intelligence in making those calls instead of just being directly weights. All right. So now, just quickly, just look at here. So we have model free, we have model based. Model free, we had Q learning and the different version in Q learning. When we have policy optimization. So as part of model free, the policy optimizations, which is going to be the next thing we're going to start today, is the types of basically reinforcement learning that they are focusing on optimizing the policy directly, like the focus is on the policy. And one of the, as you can see the names here, so policy gradient, PPO, TRPOs, like PPO, I don't know if you know, is the main algorithm that OpenAI team invented, basically, they came up with, and they used it for building the basically GPT models. So if you go to the first paper or the papers of transformers, or not the transformers, with the GPT models, basically what they basically came up with was this PPO. And then there's a TRPO, which we're going to basically start with policy gradient, PPO, TRPO. We're going to focus on those ones and how we can use those to basically train large language models. And then there's a model-based one, which the idea here is that, well, you know the environment, you know everything. And that's why, for example, the alpha zeros and like those type of models, or any gaming models that you know the full environment, basically you can basically define this like that. So now you can look at the RL algorithms in a different ways. Okay, so that it's just the definitions on how you categorize them are different. So it could be based on model. Here is based on the estates. If you have limited estates, unlimited estates, and then what type of actions you can take, and the types of algorithm will vary. When in RL we have lots of this, but there is actually also, I added also one slide at first. We didn't have it previous class. So there's also, if you want to look deeper, model-based and model-free. And model-free policy optimization we just talked about. Q learning comes here. And model-based, basically, we said alpha zero, and we have here the learn the model version. Basically, you basically try to learn those, learning the model environment. So, okay, you know there's something, I don't have it, but I want to basically learn it. All right. So now we're going to talk about policy gradient. Okay. So the idea, the key idea here is that we want to parameterize, basically learn a parameterized policy that can select an action, okay, independent of the value function. So that's the important part. Up to this point, everything we had was based on the value function, right? That's how we picked the maximum policy. Best policy was the policy that gives you the maximum, basically expected return, right? So now the idea here is that, well, what if we don't want to do that? We just, interesting images here is that in policy gradient, you say, go right? And in deep Q learning, or basically anything that is based on the action values, well, wait until let me calculate the full trajectory and see that what's the value. So you always need to look ahead, basically calculate the rewards and everything in order to make an action. In policy gradient technique here is that, well, we just want to be independent of the state value. Because the state value, you always need to have a full view of like, what's the next state value, what's the discounted value, because it's always the discounted term. So if you don't have that discounted term, it just becomes an immediate reward. So it's not value function anymore. So instead of doing this, we just want to directly take an action. So here, we're going to define these policy parameters. So our policies will have some parameters. We're going to define this theta. So as we go through the slides, when we see theta, it's for the policy parameters. And there is basically what's the chance of taking a certain action given you are in a state and under this set of parameters that you have. Like for example, if I'm in this state and this is my model, this is my neural network, what's the chance of taking this action? This is a probability, right? So, and you can also have value function if you want, but that's just optional. So now, for the optimization, so basically your goal is to optimize the policy, but we want to do it using gradient ascent, basically. So that becomes the benefit of this technique. So we basically can use gradient ascent to optimize for that, just to solve the problem iteratively. So you're going to define some cost function for that policy, parameters that you have theta, and you calculate some gradient, and you do some updates toward getting a better, basically, policy values. So now we first start by defining the basically the objective function or the goal, but overall the goal is always basically to get the maximum total return, basically, right? Now here, this is like a sampling, like an expectation value over all possible trajectories. And we have inside the bracket, we have for one trajectory, for one sample, starting from end, first going to the end, what's the total reward that I will receive? Immediate reward plus discounted, next reward plus discounted to the power of the next reward, and so on and so on. So now there are some definitions. So P of theta means a policy that has a certain parameters. This becomes the full trajectory. This tau basically is the full trajectory. You have a state, you have actions. We have a reward after taking an action in a given state. We have discount factor, and that's the gradient basically update. Okay, so far I assume this is pretty clear.
But here also we are going through all the trajectories, right? Like every available path towards the end.
So you have a trajectory, right? But we're not. No, that's a definition first. Okay. But you have a trajectory. You're independent. You are not going to depend on value function. There's two different things. Having a trajectory versus value functions are different. I think this is repeated. Yeah. Okay. So, action value function. This is just a refresher. Basically, we saw this is the action value function, state value function. We have seen this before, and as you see, the only difference between those two is that the first one is given action, the other one doesn't have a given action. So, well, there are some limitation for the overall policy gradient methods. One of the sample efficiency is poor because this is some idea about the using the old data over again or getting rid of the old data. Which one is better? The second one is more challenging here is that the distance basically in parameter space is not the same as distance in policy basically space. Now, what does that mean? When we define policy means all set of actions that you can take, right? So if you think about it from hypothetical perspective, like if you think about it from embedding perspective, the distance, basically the domain space that you have for policies, right, is where technically you need to update and pick action from. However, when we pick a policy and we parameterize it with some parameter theta, we only update with respect to theta. So we actually, technically, we are not updating in a domain space of policy. We are updating in a domain space of parameters. So those two are not technically the same. We are using it anyway, but we know that as basically, it's like a limitation. This is not the same. Okay, so the updates that we do is over thetas, not over policies, over P's basically. Okay, so now there is some idea for like a hybrid approach, and one of them is called actor-critic method, for example. Where the idea will be that what if we want to have both of them? We want to have both policy and keep the action basically a state value function. And actor-critic techniques. You have an actor. Actor is focusing on the policy that P of theta is the one that takes action based on the policy. Then you have a critic. The critic model basically says that, well, you took an action went here, and this is the value that we have. It just basically critiques the actions that the other one takes, and you use that knowledge to update basically to update the actions. Now, we will break down that later. We have the full algorithm coming up. Now, to think about the policy approximation now, so if you wanted to, in a state and you want to take an action, previously you might have a certain like a deterministic way, like I'm going to take this approach. And we say that, well, let's introduce epsilon greedy to it. Let's do some exploration. And with 20% chance, I will take a different action, for example. Now here, the idea will be that instead of doing that concept of epsilon greedy, we are going to define policies as some softmax. And the benefit of softmax is that it becomes a distribution over actions. So even an action that it's not possible under the normal policy, and maybe you could take it only with epsilon greedy, with the softmax, it still has a chance of being selected, right? So that becomes a way to being able to select other policies also, not to just always rely for same thing or doing an epsilon greedy. So, okay, now softmax policy advantage naturally converts to deterministic policy. Unlike epsilon greedy, it balances exploration and exploitation more efficiently. Okay, I think that's straightforward, but this is about like the flexible action selections, where this is also related to the safe softmax concept. So it enables more, complex probability modeling. It's basically, if you think about the traditional action value methods, they don't have flexibility. It's always like you always select the best action, you always select the same action. Here, you just have more flexibility. Now, if you, for example, this game of Tetris, if you do a policy based, basically model, the tends to play better, based on it gives you more flexibility over these actions that you want to take. Then you also can. Yeah, okay. So we can incorporate the domain or like the domain knowledge or prior knowledge in these types of model also. Because the policy, the choice of policy that you have, it's you decide on those ones. So if you know something about the environment, the domain, you can enforce it as some sort of like a function, because you pick the softmax as a function, right? So you can basically enforce some domain knowledge over there. Okay, so I'm going to take a short break on this one. I want to start this first. All right, so we're going to continue with policy gradient algorithm, but first the policy gradient theorem is basically a theoretical foundation for finding the policy gradient in policy optimization methods. It has some advantages and some disadvantages. So advantage is that it finds the optimal stochastic policy, naturally enables exploration because of that softmax that basically we're using. Effective is high dimensional and continuous space because, well, you have this also models that you use for finding the policies. Large models basically you can basically iterate over them, update the parameters. It avoids the convergence issues that argmax method has, because argmax is always picks the maximum thing, so it's kind of like has some sort of convergence issues. So these types of models are better. Well, of course, it has some disadvantage similar to any neural network or any models, like that iterative model ends up in a local convergence rather than a global convergence. Its policy evaluation will suffer from high variance as well, and also it is a slow training process. Okay, so these are kind of like the pros and cons here. Now, there are some basic key concepts here. So the overall, the cost function that we define for this policy, given some parameters, comes from this expectation value. Here, basically what we do, we move the expectation inside. So this to the same thing, you just move the expectation inside. And then this value is defined, this J of theta is defined. So now here we're going to see some new terminology. So the first one that you see, mu pi theta s. So mu is going to be some state distribution. Okay, we're going to see that is a distribution over an estates, all possible estates, for example. So that means so this mu basically tells you that if I'm in a given certain policy, right, that mu tells you that what is the chance of this being in this estate, for example. When you say, so imagine I have this, like I have this distribution, and if I pick this point to be my estate S, mu basically tells me that the value for that, like, the probability density value for that, probability function, the density function for that. So what's the chance of getting that estate? Then the second part, so this is, the first part is over all possible estates. The second part is over all possible actions, basically. And this becomes the, given you're in a state, that policy model tells you to take an action, given you're in a state. And for that action, you also have some Q value. Okay, so this becomes the new J of theta in these types of model that you see. So again, the first one starts with mu, which it's going to be a state distribution. So mu basically represent the probability of being in a state if you are started in a state S and you followed certain policy as a distribution. That can be summarized in this. So let's assume here, so we have an agent, there are 4 possible estates, state 0, state 1, state 3, and there are certain actions that you can take. So what the mu tells you that if you are in a state S0 and take an action some action, what is the chance that basically you end up here in S0 again? What's the chance you end up with S1? What's the chances end up with S2 and so on? So it's just a distribution over possible estates, given you started from S0 or certain state and you took certain action. Okay, so that's we call a state distribution.
Any action in, let's say I started in state 1. Any action I take, there is a 30% probability that I will end up in state 1 itself. Any action.
Well, it depends on how is your action defined, but could be any action, right? So I'm in a certain state and I take a certain action, and that action basically take me. Let's see, this example here is fixed. Just right, you either have left, right. So if I take a right, I go here with this certain probability. If I take a left, I go here with a certain probability.
That means mu also is dependent on actions, including state. Like
mu is also dependent on, that is correct. So we will actually see this. Second line. So mu, technically, it depends on policy and that theta, right? Because it's when you do an update, when you change your policy, update your parameters, that also will impact the actions or the state actions, state distributions that you have. It's not going to be fixed. However, when we calculate the gradient, okay, that's the important part here. If this is the J, that's the cost function that we have, the gradient of that, you will see that there is no gradient with respect to mu. By default, we know mu depends on this, but we don't update mu as part of the gradient. So only we update this part, basically the Q part, the policy part. So that's the only term that we are updating. So the mu, despite the fact we know that the state distribution depends on data, we don't use it for updating the gradients. Okay, so now because we don't use it for updating the gradient, that means, well, we basically do some sampling. You know, that means you don't need to you don't need to care about my updates, what is going to be the sample trajectory. It's always independent. I just sample series of points, series of basic data, and based on that, I update this gradient value. This term basically. So I don't need to care about this and the impact of theta. That's despite the fact that we know they are dependent. Well, we don't care about that. We just say that you just have a sample And for that sample, basically, you do some like a simulation, like a full trajectory or something, and you update these gradient values, and you use that to update your basically thetas. So the second term here, this one, the gradient of log of this is technically gradient of log likelihood. Because this is a likelihood, right? Remember, this is a likelihood. So the gradient that's technically gradient of log likelihood, similar to what you have seen in ML courses probably. Now, also for the Q function, we don't use Q function. We actually replace it with a neural network, for example. So because we don't want to deal with this other approaches that we saw at the first part of the class, that you need to have a table, you need to always have the Q value function. We want to get away from those. So here, basically, this policy is calculated in a different way in compared to the traditional methods. And also for Q function, we don't use Q function, we use a neural network to estimate what that Q function could be for us. So we have, technically we have two sets of problems. We have theta, which theta is for the policy, and we have W, which is for the model that is responsible for predicting the Q for you. So you have two different basically set of models.
What's stopping us replacing the policy with neural network itself?
I think it stops you. So feel free to do that. It actually has been done before, so yeah. Now, well, there are some challenges and some adaptation that you need to do for this technique, this type of technique also. First one, as of, I think the challenge, adjusting the policy parameters affect both action and the state distribution. However, we don't update the state distribution with the gradient. Like we don't account for that. So that's something that just to keep in mind. Now, so this policy gradient techniques, it's just kind of more like a broader term that, okay, you know, we do want to do policy optimization, but how could we learn it actually? You know, how could we basically do this? So there are two ways that we can do. We can do on policy learning. We can do off policy learning. So you can basically in this scenario, you do both conversion of basically those. You have on policy and you have off policy. Now here it becomes a bit more tricky, but the idea here is that you have for the on policy agent only takes action based on the policy. That's what it means, on policy. Okay, and it basically uses that action, take action, get some rewards, and use that rewards to update the parameters. However, we have an off-policy learning. There is another policy, another basically like a, not policy, not like a behavior policy, which you call it, like another model that we use basically for exploration. So the first one is on policy. Agent only uses that to take actions. We have another model that we want for exploration. It's kind of like a once in a while, maybe, you know, the agent basically says that, okay, I'm going to use that one to take some exploration, do some new trajectories, and also uses that basically to improve its own policy. So basically we introduced that same concept of like exploration, exploitation. Exploration becomes off policy, exploitation becomes on policy here. Okay, just one of them has a fixed policy, the other one is just some neural network, some model basically that helps us.
How is it any different from the SARS one?
Well, how you do it is different. Here you focus on policy gradient. You focus on gradient methods. You take a gradient with respect to policy, update your policy. In SARSA, it's not gradient-based models, right? So it's the types of modeling. Lots of these algorithms, they do similar things. It's just how you do it is going to be different. So, and some key points again about here is that we do direct policy optimization. We use basically gradient descent, and it's a model-free basically approach. Now, there are three types of basically algorithms that we're going to review. I think I should 4 times technically, but I have 3 here written. So one of them is going to be reinforced algorithm. The other one is going to be active critic method, and the other one is going to be PPO and TRPO. It's going to be trust region, basically policy technique also. So we start with the reinforcement one. So reinforced algorithm. It's like an earlier version of this for the policy gradient technique. The first algorithm was called reinforced. It basically what it does, it uses something called likelihood ratio. Okay, in order to basically do the policy updates. And the other one that we're going to go over is going to actor critic, which, as we talked about earlier before, it has two models. One is the actor that takes the decisions, take an action, and there's a critic basically that judges the actions, and they use this to work together to update and to learn. And then the main techniques that after that we're going to go over, and that's where the transformer, like not transformer, that the ChatGPT or those types of model were trained over, is going to be on PPO policy, proximal policy optimization. And the idea over that is that we want to update the model, but we want to ensure that the updates that we do, it's not too far from what we believed we were or what we were previously. Because you might take an update, like think about a neural network, you want to take an update, and that update is really different from previous state that you were at. And that way the model diverges from the path that it was going. Now, where the connection comes to some of this that we saw here, so there is there's going to be some terminology about, we will see that the old policy versus new policy, and you can basically think about something like this, that this becomes a new policy, like a new state that you go to the and this becomes something like old policy, not for the Q, but these equations that we have seen here, we're going to see those. So we don't want to go over the reinforced algorithm, but the reinforced algorithm basically does something like this, is an on-policy technique. It uses Monte Carlo for sampling. So you initialize with random data for the parameters that you have, and you have some learning rate, you have some discount factors. And so this basically the ensure input parameters is for reading. And here inside the convergence, what you do, you generate an episode. That means that using Monte Carlo sampling, you take a sample, you have the full episode start to the end. For every episode, basically, you go through the episode, you calculate the total reward return for that episode moving forward. That becomes GT. Using that GT, you update the value of theta. So theta becomes previous theta using basic gradient ascent plus alpha times discounted GT times the gradient of this log term, like likelihood, basically. So, and you repeat this so on and so on. So that's called reinforced algorithm. It's just simply uses that basically the log of this probability, the gradient of log of this probability times the reward, total reward times some discount factors plus the previous data that you have. And you just let this loop over and over again. So that becomes reinforced algorithm. Any question on that?
Examples on the application? Where do you generally use?
Can't tell you anything off my head.
Okay.
Just search online. All right. So it has some advantage, you have some disadvantage. Well, advantage is that it's simple, as you saw, it just that was the algorithm. You can basically write something like that and you just let it run. It's bias-free types of model. It has disadvantage, it has a high variance. And basically it's inefficient because it requires full episode. It's like a Monte Carlos, right? Why high variance? Because, well, every time you take a trajectory, you could end up with a really different reward, right? So for the same trajectory, you end up with a really high different reward. So you end up with a really large variance over your total results that you have. So that's one of the basically downsides of the reinforced technique. Now, in order to overcome something like that, the idea was that, well, let's use different types of model, and that's where we end up with actor-critic model. So actor-critic model is an on-policy method. Now, the idea here is that, as you can see in this image, there's an actor takes an action, there's a critic to judge it. That's technically what all it's going to happen. So it's just what we want to do is to combine those two, the policy gradient for actor and the value function for critic. So what will happen here is that the actor is policy gradient technique. The critic is value function based. Okay, so what does that mean? The actor wants to take an action, so it doesn't need to have any value function. It just based on some policy gradient techniques basically takes an action. But the critic, in order to say how good was that basically action, where you basically ended up as a state, it uses value function. The critic has its own value function, but actor doesn't have it. We want to combine this. You have basically the bit of both, basically both work. Now, it also, as we say, is the third line that reduces the variance of the reinforced problem. Now, let's look at the structure of this technique. So actor, it learns a policy function. It's basically a function that basically gives you the policy, giving you a state and some set of parameters. Then you have the critic based on that, basically tells you what's the value of that state. Or could you also use Q instead of V? So actor takes an action. Action basically change the environment for you, but also the same action goes to the critic. So critic will judge that, how the environment will give you a return. The environment gives you to both. So that based on that action, this is where you go. And it tells to the critic, this is where you go. So critic gets the action, gets a state that, or what was the result of the environment. Based on that, it judges the, or gives a score basically of how good was that action. Then here basically also what we can do, instead of, for the critic, instead of learning the Q function, we could also have a neural network on critic that gets action and a state as an input and makes a score for you, predicts how good or bad was that action basically. So that's more common to, instead of trying to learn it, just have a model that you can also update. So that model itself will have set of parameters W that you can update as you go. So that's the step 3 we just talked about. You take an action, it gives you a reward, it gives you a state. And step 4 is that you, it is the actor critic processes. You want to update the theta, the parameters of the policy basically model. And you do that basically where you first calculate this gradient with respect to theta, which comes from this term. This part had the theta in it, and this is the original function. So we saw this here at the beginning of the slides. See that? Okay. So on the right side, you have this gradient of the policy, and you have this Q. So instead of Q, what you see, it's a model. Like we say, we are approximating Q. Basically, what we say here, we are approximating Q with the Q, basically, what's called Q hat, that is parameterized with the parameter W. Okay, that's what it means. So anytime in RL you see that, that's kind of an approximation using some model, not an actual value. So the next step is that, well, we also want to update the critic model because critic model is also has a set of parameters. So delta W comes from this equation for critic model. Okay, so we don't want to go over there, but if you take a derivation of that, that's basically what you have. So you get the gradient with respect to the, critic. You use the gradients that you have, you update the policy-based model, the theta, you update the W, and let this basically, let the run continue. So now, the next thing we're going to talk about is actually going to be something called advantage function. Now, and this is like a much more recent, the advantage function is, I'm not sure if it came from the, no, it didn't come by the OpenAI team. I'm not sure if it came by them, but possible. But the idea of advantage function is that if you want to so you are in a state and you want to take an action. I'm interested to see that if I'm in this state and I take this action, how good is that action in general, not just for that given state, not for that time step. So advantage function basically says that Q function gives you that how good is an action and a state together, right? So, and that's for one action, one state. You take that, you say minus the value of that state. What do we know about value function? Value function is an average over everything for that state. The V is an expectation. That means how good is this state overall? I do all sort of like an exploration, how good is this state? Action, the Q just tells you that how good is this state given one action? There's a difference. So this difference basically tells you that if you are in this state and you take an action, how good is that in compared to general average value of this state? If I'm in this state and I take an action and I get 10 point reward, but the average value for that state is 8, that means the advantage is 2. I have 2 extra advantage if I take this action in compared to average value for this state. Or it could be negative. That means I don't have any advantage of taking this action. So that's terminology, that becomes like a new definition, advantage. And the way we use the advantage is that if advantage is positive, we move in the gradient direction. If advantage is negative, that means it's not good, we moved in the opposite gradient direction. So basically, now
Like a momentum or a curvature.
yeah, something similar, not exactly like that, but yeah. So basically, it measures the extra reward from an action beyond the expected value. How much extra reward I will get for this action beyond this? It could be negative, it could be positive. And also it guides the policy update based on that performance that you have. So advantage function tends to be better, but if you look at the general form, now you need a Q and you need a V. You need 2 things, right? So now the idea was that, I'm going to go back to that later. How could we basically fix that? So then we use the actor critic TD error. And instead of having both Q and V, we wrote Q with respect to V. And overall, this advantage function becomes something like this. So reward plus discounted value of the next state minus the average value of the current state. So this way, we don't need Q anymore. We only write it this way. So if you can see either of these two, if you saw with Q, that's a general advantage function. If you see it only with respect to V, that's actor critic TD error. Now, the way that we use advantage, if we go back to, unfortunately, I need to go a lot back. If we go back here, our cost function had this Q, right? So when you use advantage, instead of Q, you use advantage value. That's how we basically going to incorporate it. So if we go back here now, so instead of Q, we basically add the advantage. What's the advantage of taking certain action in a state given these parameters, for example? And for the gradient also, this basically becomes the same. So it's the same equation, we just removed Q with an advantage function. But again, just remember, advantage function, it tells you that how good is a certain action in a state in compared to average value of that state, right? That basically tells you that on average, this state that we are in it is like 10 points good. But this action has 2 points above the average. That's basically what it means. That's the advantage. So now, so this becomes actor critic TD error algorithm. It's kind of really similar to what you have seen before. Don't get distracted by terms. So you start with the random parameters and then set of parameters for the state. We basically have this discount factor here. Here is showed as with P as like set as P. We take an action based on the policy that we have. We get an action, we take the action, we observe the reward and the next state. This is the advantage function, basically. With respect to TD error, remember there's no Q here. So you calculate the advantage. Then using that advantage, you update V, a state value. Then you update theta, based on the gradient that we saw in the previous thing. Then you update P. And then you go to the next state and you repeat this loop. So you have basically two updates, one calculation, two updates, and technically three updates. So you need to also update the P value. And you let this again to loop through, just continues. So now, any question on that first? Is the advantage part, is it clear? All right, so now we're going to go to next types of algorithm. It's called Trust Region Policy Optimization, TRPO. And that's where basically we go toward the PPO. So this becomes Trust Region. Now, so this is basically what we saw so far. There's no theta here. This is supposed to be J of this J. So that's overall our goal is that to maximize this J. And this is basically could be written also this form. And then we also say that this is the advantage function. And you can also write the advantage function we saw in TD with respect to V only. Now, there is something that we're going to quickly recap here. So previously, remember if I'm not wrong, if we were in the optimization chapter, we talked about that Taylor approximation and how in second order. So basically, if you have a function like this, and if you do Taylor approximation over a function, and let's say for a certain degree, Taylor approximation looks like this. And what we used to do, we picked the minimum value, we dropped it here. So that's now our function. That's our next theta. Then we do another Taylor approximation. We pick the minimum, we drop it. That's how we can faster converge through the path. You can do the same thing now for maximization. So you have this function. This I couldn't find a better picture. So this eta theta that's supposed to be JF theta. Just use your imagination. So this red line is your J of theta. So we want to go to find the theta that maximizes that. Well, instead of directly trying to solve that, we use the same concept of Taylor approximation. We find an approximate. The blue is the approximation. Basically, it's the lower bound, right? So we find an approximation, and then we go to maximum of that. That becomes our next point. Continue until you reach the top, right? So that's overall here for min-max basically types of optimization. So you can basically use this lower bound, approximate, find the top point and continue. Now, how that being used here and why it's connected. So when we do gradient, basically gradient-based optimization, so the general form of gradient solution, they're like a line search, right? So basically you do some sort of like a line search to optimize the path. Now, what you want to see in this image here is that, so imagine you have an agent and your agent basically is supposed to go up these mountains or this cliff, and your agent takes an action, goes here, is almost at the edge of the cliff and might fall down. But the next step when it was to start, it always is still going to be in a bad region, right? So the problem with line search is that you could take an action that it basically ends up being really bad because that action is really large based on the gradient of the line, or it's like based on if you just simply do a line search, you end up with a really bad place. So a step size becomes really crucial. Now, the idea here was that in trust region basically technique is that instead of directly taking the step based on the gradient and step size, we define those circles that you see. Those are called trust regions. So at every step, there is this region. That region is some sort of like a confidence zone. If I want to take an update, how secure is the environment? If I take a larger step, will I fall down or not, right? So you define this region, it's called trust region, that you are only allowed to move within that region for the updates. And that's why we do something like this, because without doing that, every time you iterate, maybe for this sample data that you receive, all of a sudden model is like, whoa, we need to change the data that we have a lot. You don't want to have large updates. That's the idea here. We don't want the model to take a large steps updates, the data is too large. So how could we enforce that? We define that every steps, you only can take updates within a certain boundary. Boundary could expand, could shrink, depending on how confident you are in that region. So that's the idea in the trust region. Basically, trust region approach is that, as you see, the boundaries here is larger after it's smaller. So you kind of have some interaction with the environment. You have some sense of what's that trust region looks like. And based on that, you only move within that. And then next step, you do the same thing. So the idea here was that, well, we want to avoid having large, basically, updates. Now, how the algorithm has changed. So the first part, the first line, is technically the same thing that we saw in the previous slides. Okay, so there was a mu, is summation over the state, policy, and this advantage function. However, there are a couple of new terminologies that you see here, and I think I need to update the slides because I think there's so many, some like terminologies are in the wrong upper script or superscript. But anytime you see old, that refers to something related to the previous policy. Anytime you see new, that means related to the new policy. Okay, so the way that you can think about it here is that you have a policy, and that policy is that to do certain things. You want to update that policy. So the old becomes the previous timestamp policy, new is the current policy. That's the way that this two term basically comes in. Now, then this basically, we are going to do something called importance sampling. I don't know if you're familiar with it or not, but we will see more of this in the, basically when we go to image generation section and stuff like the class. But what importance sampling does that, if I have this term, okay, and it kind of like I want to reformat this, and I want to introduce a new distribution here. So I didn't have this here, you see, this two term, it didn't exist in the above line. So importance sampling, you bring that, because this technically cancels out, right? This divided by itself. But you bring it here, and when you have this here, so you keep one of them in, take one of them out, okay? So that's the idea of importance sampling. Always, when we see importance sampling, you have, let's say I have some distribution Q, then I will bring a distribution P by P, and then I basically convert this to P times Q over P, right? And then if this is a summation, for example, and then I can take this P out, this becomes expected value over P of this Q over P. So that's that. You see that more often again as we go to next chapters. But basically, this is like a way for to introduce this new distribution here. So we introduce this new distribution, and this distribution, sorry, these two terms should be P old. So P theta is new. This one, I will update the slides and I share it with you again, but this is supposed to be pi theta old, pi theta old. Okay, that means the previous policy that we have. So now, because now, as I said, you can pull one outside. So this becomes expectation value over two things. Why two things? Because we have one here, and then we have this term that comes out. So if you just look at this part, if you want to get rid of this summation, you can write it as expected value over S that comes from this distribution, right? So this becomes the expected value. Then you have this term. You want to also, that's a summation over that. You want to convert it to expected value. Expected value actions that come from old policy. So overall, what you see here now, it basically says there are two expectations. In order to calculate this cost, the J of theta, you have basically this term, this ratio, and this advantage. Ignore what's the meaning of those. I'm going to explain those, but just let's focus on the expected value. What does the expected value say? This cost comes over two summation. Okay, so the first one, and it's like a weighted sum technically. So one of them is over the state distribution. One of them is over actions that are given with respect to this. Okay, and this is the old policy. Okay? Actions that comes from theta old. Okay, so again, this pi a given s divided pi given as, it should be pi in superscript theta old. Here should be pi superscript theta old. Again, I will update the slides and show it again. But now let's understand what's inside. What we have inside. So advantage, what does it tell you? If I am looking at I'm under the old policy, advantage for the old policy, and I take an action in the estate, how much is the advantage of that action under the old policy? What was the advantage? The Q value of the action and estate minus the average value of the estate. So that basically tells you that how much advantage or how good is that action on average how good is that action in compared to average value of that estate for an old policy. Then you have this ratio. This ratio has two things. On top, on the denominator, that's for again, that's why I said these terms are like bad. This is supposed to be pi theta nu. Okay, so in the third line, this is pi theta nu. The denominator is pi theta old. Yes?
Doing KL divergence?
Not yet. We will go there.
Oh.
Yeah. So this basically is a ratio. What does this ratio tells you? If I take an action under this policy versus if I take an action under the old policy, what's the ratio of that basically? Ratio of a policy for like an action under old policy, a new policy over the action over the old policy, times the advantage basically. Okay, so that basically what it tells you. Now, that goes to what you just said. Actually, let me just read this, then we go to KL divergence. Now, so now the question here is that, well, how we decide how much updates we should do on this J? Because what we happen here is that we have two policies. One of them is policy at time now. One of them is the policy at later. Okay. So policy now is basically that pi theta old. This is pi theta new. Okay. At every step, this is kind of like a cycle. This later becomes this. All right. So every time the new policy in the next iteration becomes the old policy. And that's how we loop. Our goal is that to keep updating these policies so we get to an optimal policy. Now, the question here is that, well, how big of a step size update should I do in order to basically update my policies? The challenge that you could have here is that if you take a series of steps and you all of a sudden the new policy, the change becomes really large, you can still diverge from learning. So your new policy could be really far from your old policy based on the updates that you receive, based on the gradient updates that you receive. The question here is that could we control that could we enforce the model that you're only allowed to take steps within a certain change, basically, what's called like neighborhood. So that basically comes here to how define a maximum size. First, for the step size, we dynamically we adjust it. That becomes those trusted region circles that you saw. If the divergence between the new and current policy increases, the region shrinks. What does that mean? If you have this new policy and you had this old policy, you do a divergence among to see that how different these two distributions are from each other. If it's really different, then you shrink this trusted region because you don't want to allow to take a large steps. If they are closer to each other, that means you're more confident, you increase the trust region. You said, okay, now you can take a larger step. So you're kind of similar in a similar ratio or similar basically region. Yes.
I don't fully understand the concept of ratio of the policy.
We're going to get there. Just bear with me, we're going to get there. So if changes are stable, we basically expand the region. Now, so let's go to here. So one of the ways that we could enforce that divergence is going to be the Kale divergence, right? So if you think about the Kale divergence, we basically have this expectation over this S, basically all the states. For all the states, this is log value, right? And what we are saying here is that we want to ensure that the divergence between the two states, we want to measure it. So easiest way of measuring is like one of the ways is to do Kale divergence between two distributions. So what basically we will say here is that we want to ensure that this Kale divergence is not too large. Okay, we want to ensure that it's so small. How we do that is kind of like if you think about what you have seen probably in min-max optimization, you define a max. Our goal was to do maximization, so we want to maximize this expected value. We put subjected to Kale divergence should be less than certain value. Okay, so now let's see what does that mean. So if you think about Kale divergence, you have two distributions, the old one versus new one. And it gives you a measure of how far they are from each other. And you basically want to say that whatever is that measure should be less than this. That means if you want to maximize this, whatever theta that you find, if you replace it here, this error should be, this divergence should be less than this value, right? And that's becomes a min-max problem right now. So here, what do we do in min-max problem, or basically Lagrangian function? You bring the constraint added to or subtracted from the objective function, because this was maximization. When you bring this up, you do minus that. And beta here is what?
Parameters, Lagrangian
multipliers, right? So beta is the Lagrangian multiplier. You bring this up, multiplied by the Lagrangian multiplier. If it was minimization, this was plus, right? Because maximization, this is subtract. Now, let's go. Let's connect this here to this image that we saw before. So the basically what you see here, this line M becomes this term minus this term. Okay. So there is a C term here. So in the technically it's some sort of like a parameter. In the original paper, that's the value of C. It's just some parameters for sigma gamma over 1 minus gamma to the power of 2, just a value that we selected. Let's go one step here. That's something somewhere here. Missing in the slide. Okay, I'm missing a slide, so I will add it. But okay, now, so this is the overall basically algorithm. Now let's go back to what your friend asked. So your friend is asking basically, what is this policy over the other policy? You have two policies, and basically you're comparing the action, basically what the policy gives you. If the policies, both of them, the new and old, are similar, what will be the ratio? Becomes one, right? So this expected value becomes 1 times advantage. If your new policy is larger than old policy, from perspective of ratio, you multiply the advantage by larger things. So the smaller, it's kind of like a just ratio of comparison, how different these two policies are with respect to each other. They're either the same, or one of them is larger than the other one, or one of them is smaller than the other one. So it's kind of like a way to, and again, that's why I say that in TRPO is more like a ratio base. So it's kind of like you focus on that ratio. And then we add, I think the next thing in TRPO is that you're adding this scale divergence as a way to ensure that the updates between these two doesn't get too large. Yes.
So I had two questions from this. The first question is, I know that KL divergence is not a symmetrical function. So when we are comparing with old with new, why that order itself? Like
because you don't want your new policy to be too far from the old policy.
what about the other way around? Like old with respect to new? Like
Well, old is your gold standard, right? You compare it with respect to that. You don't reverse this, right?
so because we are applying KL divergence, not any of its other variants, because it's in the paper, that's it, right? Like there is no any other special reason we need to stick
For-
with the KL divergence only. Like there is.
No, you can try something else probably.
Because I read about like Jensen-Shannon KL divergence where it is a symmetrical.
We will have all of those in upcoming classes, but why they use scale divergence here? Why not using like a? So what he said is that like if you do Jensen-Shannon, it's technically a symmetrical divergence, like average of scale of A given B and scale of B given A. It's like an average. I mean, that's the choice of the author here. So it's
Yeah,
kind of
that's
like
fair. So just because they used it in paper, we are sticking to that, right?
I mean, I don't think that's the only reason also, but because you care about I think you need to look at the problem of, I have something and I'm trying to update it. Why I should compare this with the updates? Why I shouldn't compare the update with this? Because this is what I have, what I think is good. The way that you are saying it, you basically define that new policy and old policy, they both are the same importance. If you do Jensen. I don't think that's the case here. You have a policy that you're aware of, you want to update, you don't want to, your updates becomes too far from the current policy. I think that I don't think it's just random, the author selected KL divergence. I don't think they look at the problem that these two are the same. I think one is more important, which is the old one. It's kind of like a domain that you have.
And the second one,
Yeah.
the advantage keeps bugging me. So
How it bugs you?
yeah. So let's take an example. Like in this example, it's keep bugging me actually. So let's imagine chess, game of chess. Let's say there is a position where let's say white can make a queen sacrifice and it can get to mate basically. But if queen doesn't sacrifice, game keeps prolonging on. Let's say that's the situation it is there. But in the advantage equation, the queen sacrifice means reduction of the point value of white values, right? Like queen has 9 points in chess terminology. So in terms of points, it is losing. That means advantage is not there compared to the average, But if I sacrifice the queen, the point is less, but the game goes to win.
So what is the average value for mate?
There is no value. That's win. That's
So what's the total value you get for win?
sorry.
What's the total value you get for win?
Like
It's like
Yes, mating should.
Yeah.
Mating should have higher points.
That's what I'm trying to say.
Yeah.
So if you do, let's say I lose the queen and I get a negative, so the Q for losing the queen, also the Q, you shouldn't look at it just, Q technically is reward plus discounted value of next state. So you lose a negative reward, but then you win, I don't know, 100 points because you finished the game, correct?
But when we are replacing it with advantage, we are only focusing on like
No, this is the advantage, Q minus V. Right? So that will be the advantage function. If you want to get rid of Q, you basically write it as of R plus discounted of V of S prime minus V of S, right? So I don't know why sacrificing the queen and you still winning the game shouldn't give you the highest advantage in compared to just playing the game. Because if you think about where advantage where I can use the advantage. If I take an action right now, how good is that action in compared to average? Now, let's say I take another action. There are two actions. Compare also the other one. So I look at for the other action, what will be the advantage? So I have two advantages for action A and action B. And I select the one that gives me the highest advantage overall. Right, so it's helpful because it gives you that some idea of like how good is this action in compared to general situation, right? If you play the game and let it go, that becomes a general situation. So yeah, that winning over there, I think it should be better. Maybe in the chess game that you were saying, that the winning is like only 2 points. Okay, it's not, but I think it should make sense that it's.
so model will sacrifice the queen if it
I
loves.
mean, yes, if you can win, yes. So now, so the next algorithm we're going to talk about is going to be proximal policy optimization, PPO. Okay. Now, the idea of a PPO was that, well, we want to address some of the issues that, the gradient-based basic techniques they have, policy gradient techniques they have, especially for stability and sample efficiency. Okay, that was the idea in PPOs. So we use some ratio-based objective function, again, similar to what you saw in TRPO to avoid the large updates. But it also, so there are different format of PPOs overall, but one thing that you see in the general form, I think is the one that, again, OpenAI put, it's called clip PPO. And what they do, they basically use a clip function and to ensure that whatever ratio that we saw, that ratio of new versus old is always within that range. So you clip it. It's like there's a minus plus. You always within this, otherwise I will clip the value. So now, why? In main idea of PPO was that we wanted to be sure they're really conservative about policy updates. Why they want to be conservative about policy updates? Tends to get smaller updates have a better convergence chance. Okay. But again, similar to if you think about gradient descent, large gradient updates, they don't have much chance of convergence in compared to smaller updates. Maybe at first you take a larger steps, but then slowly you reduce the step size, right? So now this became the algorithm, that is the main loss function for the PPO. And it's technically, don't look at it like it's just probably, it was really easy to read. It technically has two parts. There's a minimum function. That means there are two pieces. You pick one of them. So the one on the left, the one on the right. The one on the left, you see this RT theta. That's the same ratio function we saw before. We just replace it so we don't see it here. Ratio function times advantage. That's the same thing we saw before, correct? So what it says basically, you pick between this and this. What's the other side? So you have the same thing, same first part repeated, but the ratio part is within something called a clip. So you pick this ratio, put it in this clip function. What the clip does, if the ratio is within this range, I clip it. If it's outside of this range, 1 minus epsilon and 1 plus epsilon, I clip it basically. So that times the same thing, advantage. So it's technically same thing is repeating. One times ratio times advantage, the other one clipped ratio times advantage. So is that clear? So if ratio is greater than 1, so basically the action is more likely to happen under the current policy, because the ratio means that, remember, if the ratio is P of new over P of old, if ratio is greater than 1, that means that it's whatever action that we want to take, the new policy gives you a higher probability in compared to the old policy. If the ratio is less than 1, well, that means that the older policy that basically have a higher probability of taking this action. So that's the action, basically advantage function, which we just saw before. And now let's try to interpret this part. So there are two things also could happen depending on the advantage function. One is that the advantage is positive. Q minus V is positive. Remember, the advantage could be that on average, like how good is this action in this state in compared to average value of this state? You either get something positive, that means it's better, or you get something negative. If the advantage is positive, if we go back to this equation is a mean function over 2 terms, right? If advantage is positive, this is positive, this is positive. So you technically have minimization over this and this times the advantage, right? So minimization over that and 1 plus theta times advantage. Does that make sense? If the advantage is negative, okay, if the advantage is negative, then in that form becomes the maximization over those two. Why? So if you think about when your goal was to do minimization, correct? If your advantage is positive, the term inside is a positive term. So you still do mean over that. If your advantage is negative, the 2 terms inside are negative, right? And what would you do? Max over that. Because you want to go to the top part, like where you get 0. So that's the only difference between advantage and disadvantage behavior. Your advantage is positive or your advantage is negative. Now, this is the overall algorithm. It's from the paper, basically. So it's called PPO clip. And again, there are, I think, like 3 different PPOs, but we just review this one. So you basically set some parameters that you have for value function, for policy function, and you do some repeat the iteration, you do some trajectory, you find the rewards, you get the advantage, you, based on this value function that you have, you update using this term, okay? And here, basically, the reason you see this is because Monte Carlo. Where you took its trajectory, the probability of trajectory is 1 over the, and then you basically fit some, what do you call it, for the second model, for this one, you do argument over this. So this one becomes the value minus reward. Because remember, you have 2 pieces. You have the policy model, data, but you also have a value model, because the value model is responsible to tell you how good is the value. If you don't learn it, then you don't know it. So we learned that value function also using some model. And the way that you learn it, you do some sort of like a basically regression. The value of the, basically the model predicted minus the reward that we received. You want this to be closer to each other. The model tells you that this state will give you 10 points. You repeat the trajectory, you got 8 points. 10 minus 8, that becomes the error. And you use that as backpropagation to update the parameters of that model. So next time it gives you a better estimate of the value function. So you have 2 models basically, and you let this to run and for basically. Any question on that? But there's no questions. Sometimes it's good, sometimes I know what's going on. All right. So that was it on the RL. Now we're going to go over the training of large models and then also focus on talk about this RLHF basically. So to just recap, we previously talked about this that, well, you could have a random model bring some small data and to try to train it and it doesn't perform well, the red line. Or you could have lots of large, basically pre-trained data, you train a pre-trained neural network, and then you bring the blue line, pre-trained network and bring the small data network and you do fine tuning. So that basically is the idea overall, like what we saw before, right? You have a model, do pre-training, and you use that for fine-tuning for a small data sets. Now, there are some core challenges that with large language model, especially we focus on the GPT model. And so the first challenge was that the GPT models, there's one token prediction at the time. That's all the models, the autoregressive model. So they lack the understanding of the instruction. That's just to understand what's the instruction that the user wants to provide. And that's basically why the earliest version of GPT, you would have seen lots of the making of facts. So they have some toxic, basically, data that they provide. And or they don't overall listen to instruction. Even the latest one, they still have these issues. Now, when we think about the concept of the training of these models, up to this point, we talked about pre-training. How we pre-train and we fine-tune and we do prompting and stuff like that. Now, we're going to focus on SFT and RLHF, basically. That is called alignment, okay? So when you hear the term alignment, it's basically the goal here is that how we can teach these models, not teach the model, maybe teach the correct word, this model to be more aligned with what user or what they're supposed to do. So basically, if you think about, for example, RAG is a way for alignment because you basically enforce the model that, not the model itself, but the knowledge that the model can answer from comes from certain region or certain basically database knowledge, but the model doesn't basically diverge. It's kind of align it with that. So now, so in order to modify the LLM's behavior, we have these human annotators or basically labelers, raters, and basically what they do, they go over this data. They first fix the data. They get rid of bad data. They get rid of, toxic data and stuff like this. So you basically prepare this data for model training. Then, this is just similar thing. So what general areas for the alignment, for example, learning from feedbacks that you want to be sure that it basically has some human interaction in it. It too follows instructions, to evaluate for AI harm, for behavior, stuff like that. That's overall for the alignment. But then when it comes to GPT, in order to address these challenges, and that's come, I think it's GPT-3 GPT-3 model first. We basically start to having the instruct GPT. So you can basically give instruction, the models are more aligned. So in GPT-3, we basically start having the supervised fine tuning, basically. The whole idea is that you want to be sure that your model is fine-tuned towards certain things that you want the model to do, to act like, okay, to behave like. We will see that later. And then we're also going to have this reward model, okay? And that's reward model is where we get to that reinforcement learning things that we just saw. How to have a model that basically, based on whatever your GPT model produced, it gets that and gives it a score, says that how good it was. And then you take that as how good it was, use it for updating the policy model that you have. Okay, so RLHF basically becomes how to refine that AI behavior through direct human feedback. That's the last part. So now, so let's just start with left, step one. So you, in supervised fine tuning, you collect some data, you pass that data to human labelers. They go through the data, they label the data for the whatever is supposed to be the output, and you basically do SFT, and you basically train, you do supervised fine tuning, you fine tune, for example, a base model here. So what you end up basically here is that this is SFT model, is the model that fine tune. So let's say OpenAI that has, again, I don't know how they did it, but let's say they have this large model, base model. Every company, you need to always have this base model. So you have this base model and you want to build a new version, a better version for certain tasks with supervised, like with instruct tuning. So maybe instead of relearning everything, you pick the previous large model that you have and you do supervised fine tuning, given set of new data with alignment and basically remove toxicity and stuff like that to be sure that the model is basically better for that task. So the output of this SFT gives you an SFT model, it's a supervised fine-tune model. Then you go here in RLHF, step 2 basically starts with, so one of the steps in RLHF is that you want to have a reward model. A reward model becomes a model that looks at the output of this text generated and says how good is that. In order to do that, if you think about it, idea becomes, the simple idea is that building a binary classification, right? Like you give 2 answers and it says that which one is better, or how much one is better, like a reward model, for example. So in the reward model, a general idea for building this reward model is that you pick the same SFT model that you have, the same supervised fine-tuned model that you have. What's the last layer of the supervised fine-tuned model in GPT? Softmax, right? Drop the softmax and add a linear layer, regression, convert it to a regression. So you pick actually the same supervised fine-tuned model. You just remove the last layer and you add a regression model, regression layer. Then you have this data, okay, that you pass to human labeler. How that data works, so human label is basically, so you pass the data to what's called a model, or I think if I'm not wrong, I don't know if in OpenAI they did use a model or not, but I assume they did. So you pass this to a model and you ask the model to repeat it 4 times, 5 times, for example. So for same basically query, you get 4 answers. You give those 4 answers to annotators as a pair. So it's kind of like if you have 4 answers, you get total 6 pairs, right? This one with that, this one with that, this one with that, so on. You give all those 6 to annotators and say that, give me, basically rank those. Tell me which one you select over the other one. Okay, so that's basically the labeling happened over there for ranking. So you basically create pairs, and among pairs, basically you see which one you prefer. So there's also this possible, there's a version that you just rank all 4s, basically like which one is top. But I think as we will go down, so I think the original paper is just you rank based on pairs of result. So now you have that data of pairs result. You pass that because that same data is query, right? It's the text with the answer that basically was selected, right? And you pass that to the reward model and basically train the last layer of the reward model to produce a score. So now the reward model, which is the same as supervised fine-tuned model with the last layer difference, instead of making a next token prediction, it just gives you 1 score. If you pass it basically this 2 basically prompt, it tells you which one is better. Like it's like or even if you do 1 prompt, it gives you a score. What should be the score of that prompt? You can use that score for ranking basically. Then it comes to step number 3. So here is where this PPO comes to play. So you want to optimize the policy. What is the policy? Is this SFT. So your SFT is the same thing that you are trying to update with the PPO. So what does that mean? That means you pick a new prompt, pass it to your supervised fine-tuned model, you produce a result. You pass the result to the reward model. Reward model tells you how good it was. And that's the reward that you saw before in basically If you think about here, we don't have it. If you think about, oh, here, so this is the same reward. Okay, so that's basically the reward that you are the model produce. How good is this action? An action here is that whatever is generated. So you use that using a policy gradient, especially PPO that we just saw, update the thetas or the weights of the policy model. And this loop continues basically. So that basically the overall architect of, again, the way that we estimate or people estimate that it has been done in OpenAI. What is available in the domain knowledge, like, or public.
Extra layers are we adding
Where?
this RLHF?
You mean for this one? I think that will be probably engineer's choice. I don't think, so none of these are publicly available to know how many layers to add. So what we know is that lots of time, the easiest or the best probably choice is rather than trying to learn a separate model, because a reward model, it should be a model that can understand the text. So you already have a model that understands the text. Just change the last maybe one layer. That becomes like I think like an architect choice. But one could be probably fine also. Question on that? So, and I think that becomes it for the supervised fine-tuning part. So you concatenate the prompt and response. You pass it to the model. Basically, you train the model that becomes just like a supervised fine-tuning process that we just talked about. You have this. You basically create now this data set for the rewards. So you create these pairs, response. You ask the humans to rank those. This is again, if you have 4, you get 6 pairs. And for each basically indicates the preference between the 2 every pair, basically. I think one of the choices probably could be why pair is the more option you have, the harder it becomes to select between answers. If you want that, be sure that your answers are good. So if you put only 2 options in front of anyone to label for you, it's much easier to select. Even if you go to 3, then it becomes harder and so on. So I think that could be one reason that they went with pairs. So, and then you go to the reward model, and again, it's you have this SFT model. You remove the last softmax layer, and you add a basically layer to or multiple layers maybe to add basically single a scalar output. You prepend the prompt to the beginning of every response, like similar to what you do in prompting, right? Prompt engineering. You bring the prompt, you add it to the beginning of the response that you have over there, and then you pass that to the model. And overall, your goal here is that so you have two basically rewards, right? So you have a reward for a certain I don't know, as a query response, and another one as a pair. And your goal is that to calculate this difference between these two. Okay. So and then your overall goal is that this is a log value, right? Log over sigmoid. What does sigmoid produce between 0 and 1? So what's the maximum of loss here? What's the minimum of loss? So this is a log. Log sigmoid maximum is 1. So log, if sigmoid is 1, what would be the log? 0. So this becomes 0. So the loss becomes 0. So the only time loss becomes 0 is basically if this difference between this basically reward of this one and reward the other one is 0. If the difference is not basically, if the sigmoid value is smaller, that log becomes larger and the error becomes basically larger. All right, so it's kind of like a, I think it's a simple sigma, like a error function, just using sigma. So now the primary objective is to basically maximize the expected reward. Same thing that we saw. So we have this model parameterized by theta, and we use PPO. policy-based gradient. So, okay, I see there's an error here again. Sorry for that. This term doesn't exist here. Yeah, so ignore this part. I will update this slide. I think that I found so many errors in it. But basically, this becomes, that's the function that you have. If you do a gradient with respect to theta, you reach basically to this technically as an expectation. Just average log gradient, basically. Now, so there's some implementation consideration. Well, this is the first one is that evaluation at the end of the generation. That means you don't evaluate first, you just generate to the end, then you evaluate. Update the data only post completion of the prompt. Don't, similar to gradients, and don't update the data midway. Just do a full pass. There's some challenges: poor quality response without per token feedback, potential issues like high reward but low coherence. That means that your model gives you a really good reward, but if you look at the text, it's like, oh, it doesn't make sense, right? It just doesn't have any coherence or value to it. And then that's where we, as a solution, basically there's another way that we use scale divergence, for example. So this becomes an example of the scale divergence, and like you have different objective function, but you similar to technically what we saw before. So you have two policies, new policy, old policy, new policy. You calculate the scale of those, and this technically is, remember, this was maximization of this subjected to this, and you brought this up, become this minus that. It's kind of like the min max problem. And this advanced formulation also for the same thing, which we added some regularization term. So, all right. So, any question on this? I assume that this part we're not learning much. It's just a gradient descent. There's a regularization term. And what we see in the formula was what we saw in the PPO, basically, PPO slides. All right. So I think that's it. So, and this is just, I put this table here. It's just the different types of transformer models and their complexity. In case you are trying to use for certain tasks for your projects, just review those. One thing that I wanted to go over first before we